layer by layer. You can even see the layers here. It is an 80 square meter or 80 square foot per floor, 800 square feet per floor, total 1600 SFT house was printed. Now, this is again done by Perry, which is one of the leaders in 3D concrete printing technology. You can see this is the largest, it's a 5-family house, 3 floors that is printed, and about 3,800 square feet, 380 square meters. And you can see here, it's done layer by layer. You can see the layers. So even architecturally, this looks very pleasing because you get to see the layers, and that has a certain beauty to it because there's a certain rhythm to the layers that are deposited. And the other interesting thing here is this entire structure was printed only in 6 weeks. So we are now starting to look at cutting down on the time of construction. So they are already starting to develop lean, because I deposit material where it is required, and essentially efficient structures which can be delivered in a very quick amount of time. Now, what about the printers themselves? There are broadly 3 types of printers. So, and again, we're talking about extrusion-based printing. You have the robotic arm printer. So this is basically a robotic arm. It can be precisely controlled. It has 6 degrees of freedoms. This nozzle can be controlled very, very precisely. And I can basically start depositing the material along any contour. So the contour is stored in the computer, and the robotic arm basically traces the contour and starts depositing material. Then you have the gantry printer. So this is you assemble a massive gantry, and you can start printing large structures. And using gantry printers, some large silos, which are basically around 15, 20 meters, have already been printed using such gantry printers. Then there are the crane printers. The crane printers are basically, the idea is that you attach it to a crane. So a lot of construction sites, particularly high-rise buildings, we use cranes for transporting materials to higher floors. So basically, this crane printer would be attached to the crane, which is used for construction, and it can be used to deposit material. Now, this is just another quick view of the robotic arm printer. This printer technology, printers are available today. Basically, this is a robotic arm. It has 6 degrees of freedom. So this particular nozzle can be moved at 6 degrees of freedom, 3 translation and 3 rotational degrees of freedom. It can even be mounted. It can be made stationary, or it can be mounted on wheels. So you see here, you have this robotic arm printer that's mounted on these belted wheel system. Now, belted wheel systems allow it to move. So you can actually move the printer in addition to having movement that's allowed by the robotic arm itself. Now, one of the applications that we are currently looking at with this belted wheel system is to print bunkers. So this particular robotic arm printer can be controlled remotely. The entire printing operation can be controlled remotely. So in the forward areas, now I can send this robotic arm printer to print a bunker for me. And I can do this sitting a few hundred feet away, so that my soldier is not in the line of fire while the printing operation is going on. And once the concrete hardens, the soldiers can go and occupy the bunker. So this is one of those remote printing jobs that can be handled very nicely with this robotic arm printer. What the robotic arm does is that it gives us a very high level of precision control on the movement. So you can do very precise jobs with it. Then you have the gantry type printer. So you see here, this is basically the print head that's mounted on a gantry. This is typically used for very large scale construction. It doesn't give you the level of control that you get with the robotic arm, but it is more suitable for large operations. Now, talking about 3D concrete printing, again, what we're talking about is extrusion-based printing. So you extrude the material and you deposit it. So there are basically a few components of a printer system. You have a mixer. From the mixer, the material is dumped into a pump. So a pump basically pressurizes the material. It is pumped through a pipe or a hose, and then this is what we call the delivery system. It's a material delivery system. It's delivering the material. It's pumping the material to the nozzle. The nozzle is basically controlled, and the movement of the nozzle is controlled. It can be controlled within the plane, so which is basically movement in the plane, and you can also tilt the nozzle and deposit the material. So you have the depositing system, material placement system, and the material itself has to be placed. Now, what are the requirements of the material itself? you cannot just take normal concrete and expect it to go through this and deliver on printing. So we often call this requirement of the material, we call the material itself as the ink. So it's almost like printing with ink, and it's called the ink that is used for printing. Very similar to what we use for our regular printing on a piece of paper. So except here, the ink is concrete. So I have to now make my concrete in such a way that it basically goes through the delivery system. Once it's pressured, it has to flow. It has to flow like a liquid. It has to go through this pipe. And sometimes the pipe systems can be a few hundred meters. So that means that this material should be able to withstand the pressure. Then it has to come out of a nozzle, and it's under high pressure. And after it comes out of the nozzle, it basically, the nozzle will force it along a contour. So nozzle will force the material to be placed along a contour like what you see here. But immediately after coming out of the nozzle, the material has to keep its shape. So whatever shape was given to it by the nozzle, it has to keep its shape. That's the first requirement. The second requirement is that I have to be able to stack material layers. So after I've printed one layer, the nozzle comes back and it starts printing more layers, as you see here. So basically, a lot of layers have been printed, and this is in real time. So if you actually look at the time difference between the bottommost layer and the top layer here, in this particular case, this is printed in our lab, this difference between the bottommost and the topmost layer is but a few minutes. So that means within a few minutes, the material at the very bottom is seeing the pressure from all these additional layers, and there is nothing holding this thing in place. It is form free, there's no form. So the material at the bottom has to be able to withstand the pressure of the additional layers. So this property is what we call buildability. So the concrete that I use in this particular printing operation, extrusion based printing, has to be able to be pumped. It should be pumped through a hose. Then it has to come out, and it has to keep its shape as it comes out of the nozzle, and it has to allow buildability. So now I have to start making concrete that basically is suitable for printing, and that gets us into engineering the mixtures. The technology for pumping is available. I'll show this in the next few slides. The technology for placement is also available. What are the most challenging task is to make concrete suitable for this printing operation. And that gets us into engineering the concrete, making concrete suitable for use in 3D printing operation. And that gets us into the domain of rheology. Now, we have to understand the flow behavior of concrete and packing of solids. Now, a lot of attention is being paid into packing of solids in the concrete mixture. So now, the ink that we need for printing, now in our case, is concrete. If I have to make concrete printable, it has to come through, it has to satisfy three requirements. One is it has to be pumpable, and that's called pumpability. So when I take concrete and I pressure it, it should be able to flow through a pipe. Now, what is the requirement there? If I try to pressure concrete, typically concrete is made up of cement, water, and aggregate. Now, water is the lightest component there. So the minute you try to pressure it, what happens typically is that the water tends to separate out. There'll be phase separation. And we cannot let that happen. We have to let concrete flow through the pipe like a homogeneous mixture. And what that requires is a material, and it has to flow through the pipe with low resistance. Otherwise, my pumping pressures will go up, and it'll make the whole process very difficult. So I need to engineer mixtures which have low viscosity and which do not allow phase separation. That means the material stays intact as I pressure it. The other property that the concrete should have is called printability and shape retention, which means immediately after coming out of the nozzle, it has to keep its shape. It whatever shape comes out of the nozzle, like what you see here, it has to keep the shape, and it has to be stable under its own weight. So here now, what we require is called high yield stress. Now, yield stress is for metals is different. This yield stress of a suspension like concrete is the stress that is required to produce flow. Higher the yield stress, more is the stress that would be required to make concrete flow. One direct correlation that we have is that yield stress correlates with slump. So higher the yield stress, higher the slump. And we all know if I have concrete with a very, higher the yield stress, lower the slump. So, and we know that if concrete has low slump, it is becomes very less workable, but it keeps its shape. So if I try to make something with a high yield stress, I start facing problems with pumpability. So these are things that now I have to balance out when I'm trying to develop this mixture. And the final requirement, like I mentioned before, is buildability. Concrete, I should be able to stack multiple layers without collapse. So you can see material here where the layers have collapsed. So what has happened as I started stacking layers, the bottom layers gave way and this structure collapsed. Whereas if you go to the back here now, we have engineered the material with buildability and we are able to stack layers and create a stacked layer structure. And what property that we have to worry about here is called thixotropy. So thixotropy is basically this internal structure build up inside the concrete. So the structure starts building up, and this is different from setting. Setting takes hours. This thixotropy is the internal structure development that takes place within a few seconds and a few minutes. So we have to start engineering this material that has thixotropic development. In other words, it starts developing a structure inside so that it starts stiffening, not setting, but stiffening, so that I can start assembling more layers. So this is a very unique or a very challenging job of mixed development where I have to balance all of these things. I have to understand what is yield stress, what is viscosity, what is thixotropy of the material, and engineer a material that is suitable, an ink that is suitable for printing. Now, the issue, of course, that we have here is that we're dealing with concrete, and this is what my material looks like. And we're all very comfortable with concrete. We're now casting concrete. We have ready mix concrete that's available. But as you know very well, how do I take this fellow, which looks very coarse? It is difficult to make it to flow, and started to behave in this manner where it's basically creamy smooth. It comes out. I'm able to extrude it. It keeps its shape, and then I'm able to build multiple layers. So here, a lot of research work is happening here now. We're starting to understand what is concrete, and if you look at concrete, it basically I can break it up into paste and the aggregate content, and I can think of concrete as aggregate suspended in paste. The paste itself is cement and water and whatever else I add as cementitious material. This the rheology of the paste becomes very, very important. I have to understand the rheology of the paste to create a mixture that is pumpable, so I can pump the mixture, that is printable so that it comes out and it keeps its shape, and that is buildable. That means it allows multiple layers to be built one on top of the other, and all of that is achieved by controlling the rheology of the paste. Now we have to understand what is rheology. Rheology is basically the behavior of fluids. And traditionally, as civil engineers, we do not understand or we do not spend the time to understand fluid behavior. The only fluid that we understand is water because we use it in hydrology. But here we have a very complex fluid. We need to understand how it behaves when I apply shear stress, because cement paste is not a Newtonian fluid. Water is a Newtonian fluid. So here we need to understand how this material flows and also aggregate content. The packing of the aggregate now plays a very key role in determining the flow behavior of concrete. And what I need to deliver on is basically something, a concrete mixture, a concrete composition that will allow pressurized flow without segregation. It will set with shape retention on stopping the flow. So the minute it comes out, it basically keeps its shape and allows more materials, more layers to be stacked on. Now, coming to pumping, we are not new to pumping. In fact, today we have managed to develop concrete mixtures that can be pumped. And I'll just give you one example. Burj Khalifa concrete was pumped to a height of 600 meters. And special concrete mixes were developed that could withstand the pressure head of more than 600 meters. So concrete could be pumped. So the pumping technology exists today. I don't need to reinvent this. This is already in use. Concrete compositions also exist. Concrete mixture compositions that can be pumped for 600 meters. That's also available. Similarly, One World Trade Center. Here, concrete was pumped to a height of 103 stories. Now, So clearly we have the pumping technology, but that is only one part of the requirement. Now I have to start looking at the other parts of the requirement. And I just wanted to show this to you that in One World Trade Center, there were specific requirements that are put in place that concrete up to 40 floors, the strength that they required was 80 to 95 MPa, upper floors was 60 to 7 MPa compressive strength. And the requirement that was placed on the concrete that it concrete which is 80 MPa in compressive strength was to be pumpable for at least 40 floors. So such things have been done, and this is not new. This was done in 2005, 2006. So pumping technology exists. We also now know how to make concretes that are pumpable, that can withstand the pressure that will basically flow through a pipe and without segregation. So that is something that's available. What else do I need from my concrete? The ideal concrete for printing is that it should be. Yeah.
Excuse me. Is it possible to share your video answer? Your video is off, sir.
My video is on.
Answer.
It is on. Is it not moving? What is happening?
Your video is not visible. Presentation is coming, sir. Your face is not visible.
No, I've deliberately turned it off just to save on the bandwidth.
Right, sir. Carry on. Thank you.
Okay. Yeah. Okay. Now, sorry. So now, what I need is material that will be homogeneous. It will flow under pressure and stay homogeneous. It will set on demand. So I want the material to come out of the nozzle. Once it has been, once it exits the nozzle, it should keep its shape. So that is another essential requirement. It gains strength rapidly. So it should go through setting and gain strength very rapidly. Of course, we want material that's durable. This is a universal requirement where we say the material should look new without maintenance, and the entire thing has to be done at a low cost. I can't just start making it very expensive. And what we realize as we go through this is that the basic combinatorics of cement, water, aggregate cannot do this. So I cannot look at IS 10262 and look for guidance on how to develop a concrete mixture that is suitable for printing. What we need to do is revisit the mixed design principles. Additives and admixtures become inevitable. I have to start using a lot of additives and admixtures. I have to start looking at packing and multi-scale concepts. So I have to now look at concrete as an engineered material, where I engineer the material by packing, looking at multi-scale effects within concrete, and develop a mixture that is scientifically developed so that it gives me the required performance. Right. So now, like I said, with concrete printing, especially what we're talking about extrusion-based layer deposition, delivery systems are available. Today, we have very sophisticated delivery systems that are available for 3D printing, whether it is robotic arm or gantry. And these have been adopted from what was developed by mechanical engineers 2 decades ago. And we are basically adapting it to our use because we have to scale it up. What they were doing was on a smaller scale. We have to do it on a much larger scale. The real challenge lies in the ink, the material that is suitable for use. And what we need is I need to develop a concrete that basically resembles toothpaste. Now, if you think about toothpaste, when I pressure the tube, the toothpaste flows out of the nozzle. So this is toothpaste flowing out of the nozzle. Then the back end of the tube is pressurized. It comes out of the tube and it keeps its shape. And that's what I need to deliver on. And additionally, not only does it keep its shape, but suppose now I was to print one layer with toothpaste, come back and print another layer on the same layer and keep printing layers on one on top of the other. The layer at the bottom should not collapse. It should basically be able to sustain the weight of the additional layers. That's what I need to deliver on. And we basically now are starting to look at this in a very scientific manner, trying to develop mixtures by understanding the rheology of cement paste and developing concrete mixtures that will deliver on all of these things. So we are now looking at rheology control. So we're talking about viscosity control, developing materials which have high yield stress, and we are looking at bringing in a lot of additives that we are comfortable with, like water reducers, viscosity modifying admixtures, retarders. All of these are now becoming very fine, but microfines are becoming very essential. So we also pack the material properly, and packing concepts have come to the fore. Some of the materials that we're using are very non-traditional. So we're starting to use materials like nano clay like montmorillonite, bentonite clays. These have excellent buildability property because they give us this structuration inside the material that allows me to develop a material that's buildable. Now, one of the things that I wanted to present is that we are already developing engineered stiff mixes. So right now technology for form-free construction, casting concrete without the use of form is already in use, like slip forming that we use for pavements. So this is a slip forming machine that is used for pavement. And you see, we have developed concrete mixes which have this property of shape retention. That means I dump concrete in here and it comes out of this the paver machine in a very stiff form, and it's able to keep its shape. So this is engineered stiff mix. I need to develop something along these lines, a material that basically comes out in a very stiff form, keeps its shape. That's what I need to develop. And the way they do it for this particular thing, it's also called PQC, pavement quality concrete, or pavement grade concrete. Except now this is pavement grade concrete that is qualified for use in slip forming. And they use a lot of water reducers, microfines, and water reducers here. Another place where high performance concrete is used, where shape retention is expected, and that is in precasting. So if you look at a hollow core slab, this is a very stiff mix. Concrete essentially is extruded. So you see concrete is dumped here. It goes through this hopper here. It comes out, and when it is extruded, it's basically pushed from behind. It is extruded with this shape, with the holes, and the material is supposed to keep its shape. The hole cannot collapse on itself. So right now we have technology that's available that gives me stiff mixes that can basically keep their shape. So this is one of the essential requirements. But I have to take this material which is stiff, and it should also meet the requirement of pumpability, that I should be able to pump it. If you look at the placement system here, there's no pumping involved. Material is simply dumped in here. It is forced through this the nozzle here, and it is extruded with vibration. So heavy vibration is applied here before it's placed. What I require is the material should keep its shape. That means it has to be stiff, but it should also be pumpable. So basically now what I have to do is combine what I have in the form of pumpable mix and make it keep its shape. So these are now, if you think about it, two opposite requirements. Pumpability requires a fluid mix, whereas this shape retention requires a stiff mix. So I really have to have material that will flow under pressure. Then once it comes to rest, it will keep its shape. So this is the challenging requirement of printing. And that's only two of the three requirements. The third requirement is basically buildability, where I have to have the material, once I've extruded one layer, it should be able to take the weight of multiple layers. So that means that the material should be fluid enough that I can pump it. Once it comes out of the nozzle, it has to keep its shape. And we know that a stiff material keeps its shape. That means the minute it comes out of the nozzle, it should become stiff. Whereas while I'm pressuring it, it should be fluid. So this is the kind of engineering I have to do. And the material that's come out of the nozzle should be stiff, but the stiffness should keep on increasing. And that is this property of thixotropy, which allows me to give it buildability. And this thixotropy, if you visualize, is schematically shown here. So a material that is stiff is shown in the form of a cube. Obviously, when I try to force a cube to roll, it is not going to roll. But the minute it comes down this slide, it turns into a sphere. And then the minute it exits the ramp and it comes to rest on top of the solid surface, it again turns into a cube, which has very good shape retention. This is the kind of material I have to engineer that basically gives the flow property that is required based on where it is located. If I pressure the material, it should start flowing. The minute I let go of the pressure, it should become stiff and keep its shape. And not just that, but it should continue to gain in stiffness so that I can put multiple layers one on top of the other. So this is what I need to do with my mix that is suitable for printing. I have to engineer thixotropy. That means it should have a high thixotropy. It should have low viscosity so that I can pump it. That means it's fluid. It should have a high yield stress. High yield stress would mean it basically has a high resistance to flow. But this is when I remove the pressure. So it comes out of the nozzle and it has to have a yield stress so that it can keep its shape. And now we're talking about developing concrete mixes suitable for printing, which are very, very complex. So we now use water reducers, nano and microfines, retarders, materials like clays, then microfines, and we're talking about packing concepts. All of these go into developing a good mix that can be printed. So just to show you thixotropy is basically this property where when you shear a material, it becomes fluid. And when you let go of the shear, it stiffens up. So that is the kind of property that we need to engineer. And today now we are starting to add material that give this thixotropic property to concrete. And clays we find are excellent in giving this thixotropic property. Now, we're also looking at paste content and packing concepts in order to develop material that will flow easily through a pipe, come out and keep its shape. And with that, now we are able to start developing concrete mixes that can be printed. So, and these mixes have now been developed worldwide. A lot of people have worked, and this knowledge has now developed to a point where we can start assembling this. In our lab, we have now concrete mixes that can be printed, and we can assemble. What I'm showing you here is a structural element. And it's a double wall system. So you can see two walls with a batten in between. And this is developed by assembling multiple layers. And we are able to print 1.5 meters to 2 meters height samples. And so this was done in a span of half an hour. So the bottommost layer has still not set, but it has stiffened enough that it can take the weight of the additional layers on top. Now, like I said, the challenges now, most of the things have already been required. Pumping and placing systems are available, and we are able to deliver on printing. These are the printers that are available. They are available commercially, readily, which is available. Software for controlling the delivery system, everything is available today. Robotic arm systems are also available. These are developed by the same companies that have developed robotic arms for welding and other processes. Now, that was about the material development. What are the other challenges in use of 3D concrete printing? Assuming I have a material that allows me to print, assuming I have a printing system that allows me to pump the material, a placement delivery system that allows me to deposit the material in layers, assuming I have all of that, assuming I'm able to print concrete. The other challenges that I have today are integration of reinforcement. Everything I've talked about so far is only about concrete, but we know that concrete by itself is not tenable. I cannot use it in structure. So we have to talk about reinforcement integration. The other big challenge we have is determination of structural performance. Typically, we take a cube of concrete, we determine the compressive strength, and from that, we are able to determine the behavior of an entire structure. The issue that I have is in printed structure, material is deposited in layers. Therefore, it will exhibit what is known as anisotropy. It will have direction dependent behavior. So I have to be able to determine what is this material property in the different directions and be able to come up with predictive schemes that will allow me to predict the behavior of a structure. And finally, we're talking about continuity in the structures. I need to worry about, since I have multiple layers, I have to make sure that each layer is bonded to the other layers. So I have to have continuity between the layers. Otherwise, there is no structure. And suppose I build the structure in components, and that's what we're doing right now, then we need to have continuity between the different components. So in terms of challenges with the reinforcement, people are working on different methodologies, co-printing of steel and concrete. So there's a group in Switzerland that's working on this. The other way that people are looking at 3D concrete printing is to use the concrete print as a formwork. Then you can insert reinforcement and pour concrete. What advantage again with this is I can print the formwork in any shape I want. The third methodology people are working on is with the use of internal reinforcement in the form of fiber reinforcement. So I can print concrete that has fiber reinforcement. And basically, the internal reinforcement does the same job as putting steel rebar or steel reinforcement bar inside concrete. So different methodologies are being looked at for printing with steel. The Chinese are making very rapid advances in integrating reinforcement with concrete. So different like this is a technology that is developed by Japanese, where they basically have this filament winding machine, a robotic arm that winds a steel high strength steel filament around the printed material, and you print concrete around it. Then there is this methodology developed in Germany where they basically deposit fibers along the path. And the fibers are deposited between the layers. Now you can control exactly how much fibers you want to deposit. So wherever you have high tensile requirement, stresses are high, you deposit more fibers. Then this is the co-printing of steel and concrete. This is being experimented with in Switzerland. So different, and this is another methodology developed in Japan, where they insert reinforcement. So you print a concrete structure and steel reinforcement is inserted inside the printed structure used by another robotic arm. So now a lot of technology in the form of robotic arms, etc., coming into play, where you have printing of concrete and then you're trying to integrate steel with it to make concrete structures which have reinforcement in there. So now coming to the determination of structural performance. So remember I said that there is anisotropy in the material property. So if you look at a typical printed structure, it has multiple layers. Now, if I was to core this material, or if I was to cut cubes out of it, you can see that the direction in which the material is printed, material will be nicely compacted. Then across the layers, I will get a different property. And that is what we are now trying to understand, to see what is this anisotropy, what is the weak direction of the material, and how do we now orient the material and the structure so that I put the strong direction of the material along the direction of the structure where I have high stresses. So this is the work that we are currently undertaking, where we're trying to understand this directional behavior of the material and try to understand how that influences the structural response. So we are printing this truss type of structures and with different directions of printing to understand how that would influence the structural response. Now, finally, the continuity between layers and between different components. So one of the things, like I said, is when you have multiple layers, the bond between the multiple different layers becomes very important. If the two layers don't bond together, then you don't get composite action. That means the entire structure doesn't behave like one. So one technology or one thing people are looking at is bonding agents, applying a bonding agent here between the layers. So I print a layer, apply bonding agent, and then print another layer. Another way people are looking at is penetration reinforcement. So this penetration reinforcement is introduced, and then you print around the penetration reinforcement. Now, in terms of use of printing technology, one of the ways that we are looking at very actively is what is called off-site printing. So I print components off-site, I bring them to the site, and then I post-tension them for continuity. So what you see here is a bridge. And if you can see, there are different segments. Each of these segments was printed individually, and then they were brought to the site and they're post-tensioned here. So here now, the continuity between the elements is provided by the post tensioning, and the element itself now I can optimize because I'm printing it. It doesn't have to be rectangular, it doesn't have to be a box shaped structure, it can be any shape that I optimize, and I bring these individual components to the site, I post tension them together for continuity. Now, so these are the different the technologies that are being developed, the different ways people are looking to overcome the challenges that are there. What is the biggest challenge in development of this technology is that if we want this technology to mature and become suitable for use in construction, we have to, the essential thing that is stopping us from doing it is the human factor. We have to start thinking outside outside our silos. The way we look at civil engineering, we become very comfortable doing the way things have been done for perhaps a century. We have to move out of that box and start thinking about manufacturing, essentially bringing in digital technology. And the only way 3D printing will succeed is if we bring in confluence of technology, which means that we should be willing to adopt and adapt technology for use. There are certain other challenges with 3D concrete printing. One is copyright and IP issues. This is a very major challenge. People who develop material designs, those who develop printing technology, most of them have patented this. So today, if you want to use it, use of this technology comes with a heavy fee that you have to pay. And this is one of the big challenges. The other big challenge with 3D concrete printing is codes of practice. If I want to print a structure today, what stops me from doing it is lack of standardization. There are no standards that tell me how to exactly adopt this. It's an emerging technology, and standards are still being developed. Now, those are all the challenges, the issues that we have. In the next few slides, what I want to talk about are the opportunities that we have. Now, the opportunities that we have is lean construction. If I make this technology practical, what I can do is I can start developing structures using this concept called material follows force. Material follows force is a very simple concept. Suppose I have this beam here subjected to 3-point loading. If you look at it, the flow of forces within the beam would be such that it will develop a concrete compression arch. So you get a compression arch along here, and you need a tie along here. So the tie is provided in the form of a reinforcement bar or reinforcement bars that are placed at the bottom. So it's like a tied arch. You get a compression arch, which is tied by reinforcement. Now, you can actually optimize this and have a beam where you remove all the unnecessary material that does not contribute to the arch and come up with something that looks like this. This is called, the process itself is called topology optimization. I can optimize the material and come up with this truss-shaped structure. Now, truss will have these struts, and the struts will be in compression. Of course, I need to balance it with a tension tie here at the bottom. Now, this topology optimized structure will essentially give me the same stiffness as this real beam, but at a fraction of the weight. So I deposit material where it is required. I get lightweight structures, reduced reinforcement because I don't need to provide reinforcement where it's not required, and reduce the wastage and give you structures which are fraction of the weight, which leads to more efficient use of material. So this is a major advantage of 3D concrete printing. Now, like I said, current state of practice with 3D concrete printing, we have on-site printing and off-site printing. So if I want to do a large printing, I can take up a gantry printer and actually print the entire structure. What is more popular these days is what we call off-site printing. So in off-site printing, I print elements off-site, take them to the site, and I will integrate them. Now, I can basically use off-site printing to print formwork if I want. So if I have some challenging shape, I can print formwork using this 3D concrete printing and simply pour concrete into that. Now I can offsite print these elements and integrate it in just the same way I do precast construction. The advantage again over precast construction is I am not limited to rectilinear shapes. I can print this material, these elements in any shape I want. But today, because we are not at a scale where we are able to scale up things to that level, we are not yet in a position where this technology is challenging precast or any other form of construction. Precast and some of these other technologies have been in existence for a long time. This printing is relatively new. It's all started within the last decade. But as time progresses, as printers become more readily available, as material is developed, it's a matter of time before it starts challenging precast in a very major way. I just want to show you offsite printing. This is an offsite printed structure that we have printed, working with a company that specializes in 3D printing. They have developed their own robotic arm printer. And you can see we have printed these shapes. They're brought to the site and now they're integrated. So we basically have left places. This is a double form system, double wall system with gaps in between. And we can bring these elements together and we have conventional reinforcement. So we'll pour concrete here, which basically provides the continuity. And as you can see here, the reinforced concrete elements essentially form the structural elements, while this double wall system becomes the wall, which is a non-structural wall. And with this, now I don't need formwork for the columns because basically the formwork comes in the printed shape. pour concrete in here just by putting reinforcement in there. The double wall system gives me better thermal and acoustic properties. And therefore, the whole thing can be done very rapidly because I can print these elements off-site, bring them to the site, and just simply integrate them with the existing form. So then the other thing I said is I can off-site print formwork, which can be integrated. And I showed you an example in the previous slide. Several niche applications that are being taken up. Here is an example of lightweight bridges. So I can, like I said, I talked about this before. These are individual segments that are printed. And the segments are brought together, as you see here, and they're post-tension. So now I have a bridge that's ready to use. So these are like precast elements, except now, if you look at this shape, casting them would be very difficult. So they're printed. And I can simply precast them, and I have a bridge that is ready to use. So this is another technology or another application that's being looked at very, very seriously with printing technology. Then we are also looking at low carbon materials. So being able to print with geopolymer concretes, cement-free binders. We can develop these wall panels. So these can be non-structural wall panels, double wall systems, or double pane systems, which give us high acoustic and thermal comfort. I can fill these gaps with a material that has high thermal and acoustic insulation properties and use it as a non-structural infill wall. The advantage is I can print walls very quickly. I can print these up very, very quickly and give them whatever shape that is required and supply them to the site. The final thing is that with printing, I'm not limited to rectilinear shapes. Not just that, I can print in multiple shapes. So I can give geometric finishes, and that's what the architects are all excited about. So I can actually print walls with different textures and features. And rather than having a plain wall, I can print this feature. And that, I think, architecturally is being looked at very seriously in providing the required beauty. And of course, since I'm not limited to rectilinear shapes, I can start thinking about having shapes which are curved, shells and all these structures. Once the technology matures enough, I should be able to print these complicated shapes. Now, one of the biggest opportunities available in 3D concrete printing is startups. And I'm going to throw this as an idea to all the young people who are there. It's a very new technology. And we are seeing most of the development that's happening in 3D printing is primarily through startups. So young people who are tech savvy are coming together. They are basically developing solutions, different printing solutions. It's still a very fresh field. So there are no big players who are there yet, at least in the technology development front. There are very few. So this is a technology that is ripe for getting into starting something, and therefore it's ideal for young entrepreneurs. But we are working with a group of young entrepreneurs who have started a company called Simply Forge Creations, and they now have developed their own printer. They have they're starting to get into developing serious solutions with 3D concrete printing. So now the challenges with the 3D concrete printing, like I said, standardization, terminology, mixed design procedures, these don't exist yet. But American Concrete Institute, RILEM, these are agencies that are starting to work on it. And it's a matter of time before we start getting standards, codes, which will help us design concrete mixtures, even for use that can be pumped, printed, and even will have buildability. That will be standardized. Then even design procedures with the use of these materials are being standardized. So as design procedures are being developed, we realize that joints between different printed elements, this has to be looked at. Bond with reinforcement, this has to be looked at. These are all research topics. Prediction of structural performance. So if I have a printed structure, what is its performance going to be, particularly from an earthquake point of view, seismic, wind? So these are things that we need data, and that is being researched. These are hot areas of research right now. I just wanted to leave you with this last slide where we have developed this concept of form optimization. And this basically follows this idea of material follows force. So using this now, we have developed this concept of a tide arch. And this tied arch concept can be extended to print very lightweight bridges that will give you the same level of stiffness as a solid beam or a solid piece of concrete at a fraction of the weight. And we have actually demonstrated this by printing 8 meters. So this is an 8-meter span, the pedestrian bridge that we have printed on our campus. It's actually installed on our campus. It is designed for pedestrian loads as per IRC standards. And if I was to compare the weight, this comes out to a fraction of the weight that I would get if I was using solid concrete beams or girders. And it delivers the same level of stiffness and performance in terms of vibration and other things. So you can see the arch here. Now, initially when we designed the structure, we designed it as a tied arch, which means there's a tension element running across. But then we removed the tension element and simply provided a stiff abutment on both sides, which basically gives me the same effect as a tying of these elements. And you can see this is the deck. The deck itself was cast in situ. This is the structural part here. This element here, this entire element, as you can see here, you can see the struts here. These were all printed. So they're basically printed with multiple layers. It is about 1.5 meters wide, 8 meters in span. So this is what we have delivered on our campus. This is on the campus of IIT Hyderabad. Now, so with this, I would like to conclude my talk and maybe leave with on a positive note, and that is civil engineering and particularly structural engineering. I think we have been shy. We have been very wary of technology, digitalization, and perhaps 3D concrete printing is that Trojan horse that will force us to bring in digitalization in our construction. So with that, I leave you. I'll open the floor for questions, and thank you for patiently listening to my talk.
Thank you, sir. Thank you very much for your presentation. There are some questions posted in chat box, sir. Can I ask, sir?
Sure.
Yes. Engineer Venugopal from Kakinada Center, he posted 5 questions, sir. What is the efficiency of concrete joints while connecting to different 3D elements, and what is the maintenance cost?
And this is something I covered in one of my slides. This, we don't have data yet. So as we do research, all this data will come forward. So then we'll be able to answer this with certainty. Right now, yes, we don't have a very clear answer, particularly about durability. Data is being generated, and with time, we'll be able to answer this in a more precise manner.
In the starting itself, he posted the questions, sir. Before the webinar, he have posted his queries. So I will ask again. Is it possible to create with RCC 3D printing?
RCC, yes. Currently, integrating steel is a major challenge. So we cannot do it in the conventional manner. So we are looking at integrating reinforcement in multiple forms. One is to use steel, flexible steel. So we're looking at printing concrete with steel, but steel then is provided in the form of flexible wires, high-strength steel wires. I can print them with those. Or internal reinforcement in the form of fibers that are added to concrete. Or co-printing steel with concrete. And that these are all different things that people are working on. And it is still some time before that was. And
what is the maximum size for each element? That is length, width, and depth.
Right now, if I was to use a gantry printer, using gantry printers, people have been able to print 10-meter diameter silos. No issue.
And the 4th question is it economical or not to compare with conventional concrete elements?
Correct. Currently, it is more expensive. The reason is the technology is right now provided only by a few providers. The material is also more expensive because you have to order the material, and therefore the people who are supplying the material, they charge you more. So right now it is more expensive. Savings are in the form of lighter structures. So I can actually print structures, placing material exactly where I want. So I get a more efficient layout of material, which is lightweight. So I save on the material cost. Now, with time, as technology matures, then the cost of production will go down. This is like any new technology. When the technology is new, it is expensive. With time, what happens is we learn how to scale it up, and the technology itself becomes cheaper. So that's bound to happen. Today, yes, it is expensive.
Yes, sir. The fifth question is also similar. Is it advisable to small towns in respect of the investment on 3D printing units?
Again, it's the right now what we're looking at is because we do not have design standards, so I cannot use it in a lot of structural applications, because everybody is going to challenge it. If or anybody will challenge it, they'll say there's no design code. So that is a major shortcoming. But as design codes become available, as we become more comfortable with the technology, as we learn how to integrate steel, uh, it will become more commonplace. So at this point of time, the usage of 3D concrete printing is limited to niche applications, to specialized applications. So we are looking at several applications. A lot of applications involve the use of non-structural walls, facade elements, architectural features. So these are things that really don't have a direct structural code requirement. So we're able to get into that right away. With time, eventually, of course, even the structural applications will develop, and then, of course, it will be like any other technology. The costs would have to be worked out. So I can give an example of precasting. Now, precasting it now is quite a mature technology. It's quite established. We're starting to use precasting everywhere. Whether that is suitable for small towns, the same set of questions will be essentially will be applicable to 3D printing as well.
Yes, sir. Mr. Swapnil posted two questions in the chat box, sir. Up to what size of aggregate you have used in your printable mix at IITH?
That's a very good question. Actually, right now our limitation is 4 millimeters. So right now we are able to print up to 4 millimeter aggregate. And the limitation has to do with the pumping system. So the pumping systems we are using right now, if I start using larger aggregate, I get into a problem with the pumping system. So and the pumps are being developed. So now we are working with pump manufacturers to see if we can actually incorporate larger aggregate. So our limitation right now with our pump is 4 millimeters, but now the Chinese are starting to print concrete 20 mm aggregate, and also in Europe they have now printing solutions available for up to 10 mm aggregate.
One more question, sir, from Swapnil itself. As rheology is highly influenced by even a small change in a material or even source of material as well. So to develop standards for the rheology characterization, how we can overcome these challenges?
Well, let me take one step back, and that is today we accept self-compacting, self-consolidating concrete as a standard material. Just 10 years back, SEC was still considered an exotic material. Today, in fact, I can order SEC, get SEC from RNC suppliers. They're starting to supply. And rheology control of concrete started with SEC. And today it has come to a point where we understand precisely how I control the rheology so I can produce concrete that is self-leveling. So that is one attribute of concrete which levels by itself. And that also required rheology control. And that also required understanding the local materials. So I'll just give you an example. When we were doing SEC, in fact, in the practically the entire south of India, river sand was banned, and this robo sand or manufactured sand was essentially became the norm. But we are able to make SEC with even the manufactured sand. And SEC requires a very precise control of fines to get the packing and the rheology control that we want. But because we understood the effect, we have developed a code. Now IS 10262 gives us guidance on how to do SEC. So we are able to use the proper admixtures, the proper aggregate, go for proper packing, understanding the role of fines, and we are able to deliver on SEC, even with the use of robo sand or manufactured sand. So something similar will happen even with printing. That right now in the laboratory stage, we use nice clean material, everything is nicely regulated. But once we standardize it, so at the standardization stage, all these variabilities will be considered and we'll have a standard. We can follow that standard to develop a concrete which with the maximum aggregate size, which will give you pumpability, printability, and buildability. So you can use it for printing.
Yes, sir. There is a question from Puneet Rai. Can GFRP rebars used as tension members where no bent up bars are used?
Same as the steel bars. So basically, if the bar is stiff, I'll have to think about how to print it with concrete. If it is flexible, then I can use it directly in printing. So there are people who are using carbon tape and they're printing concrete with the carbon tape in it. And the carbon tape basically acts like a reinforcement. So that is certainly available. But with FRP bars, I can use it just the way I would use it in normal concrete. My issue would be to get good bond between the printed concrete layers and the FRP.
Yes, sir. I have a few queries, sir. Is there any height limitations to be casted per day in layers, sir, in 3D printing technology?
The limitation of height would be the material. How much stress can it take? Suppose I was to print a 2-meter high a component, which is made up of multiple layers. The bottommost layer should be able to take the weight of 2 meters of material above it. And remember, we don't have any formwork. That material is as it comes out of the printer. It should be able to sustain the weight of the added layers. And so that is something that would be required from the material. And as long as you can develop a material that is able to withstand that, you can print more. Now, typically with the current print speeds that we have and the printing machines that we have, printing something that is 2 meters high, let's say, which has a complicated contour, would take somewhere, I would say, around half an hour to 1 hour. Now, this is before setting happens. Setting happens around 2 hours and later. So that's the first thing that we have. So most printers today, I think we are doing 1 to 2 meter heights. We wait and then print additional layers. That's typically what is done.
Sir, one more question, sir. Is there height limitations of the structure, sir? Overall height restriction?
There is no height restriction currently, but there is a BIS standard that is being developed by the precast committee, where at the current this thing they want to limit the height to 12 meters or 15 meters. I think that's what they want to do. And the reason they're limiting it is because we do not have data on the seismic performance of printed structures. So that is the only limitation. Otherwise, there is no other limitation.
Okay, sir. Yes, sir. Yes, sir. Continue, sir.
Sir, this is Dr. Narasimha, sir. Sir, I have one question, sir, regarding. Hello, sir. Subramaniam,
yeah.
Sir.
Yes.
Audible, sir. Audible,
sir. Regarding, I have seen one from one of the slides regarding the fiber reinforcement was printed as one of the reinforcement layers. Suppose it was added to the concrete mixture. Is it improves the thixotropy of the concrete mixture, and also is it will be sufficient for that to take care of the tensile stresses that is coming on it?
Yeah, so the thing is, adding fibers does not improve the thixotropy. Adding fibers basically is done as internal reinforcement to take tensile stresses once the concrete hardens. So it really doesn't help with thixotropy. In fact, one of the bigger challenges with fibers is that they tend to bunch up, and printing material without choking or clogging the nozzle, that is a challenge. So right now we're looking at different fibers, those which will not clog the nozzle and yet are stiff enough that they give us the structural properties of high carrying tensile force even after cracking. So that is something that is being looked at. In fact, the Australians have also managed to print UHPC. So they're actually printing ultra high performance concrete, which is a very high compressive strength and also very high volume fraction of fibers. So it's basically, if you can do that, it's like a structural material itself. You really don't need steel reinforcement. So it's certainly possible. And now I would say that the Australians claim that they have printable UHPC mixes that you can print using normal printers.
And my second question is there, sir. Regarding the understanding of the anisotropy of the material, generally in the case of plies, that is the plywoods, we generally come across with the situation of taking the Poisson effects into the consideration. Shall we include the same effects in the similar design philosophy for the 3D printed concrete also?
Yes, it's like any other concrete. The only issue, I mean, if I just take the material in one layer, it's like any other concrete. The only thing that is different is that when I cast concrete, I'm not directionally orienting it. I simply pour concrete and it spreads. So I'm not giving it any directional preference. Whereas when I'm printing it, even if I take one layer, I'm basically extruding that layer. So what is happening is the material is getting compacted in one direction. So in one direction, I expect the material to be stiffer and stronger compared to the other two directions. So there is one level of directionality of the material based on the compaction produced in the extrusion process. That's one. The other thing is I have multiple layers. And if you look at the layered structure, now if I test it by applying compression this way, or if I flip it and apply compression this way, or if I was to test it like a beam, when I apply force this way and I have multiple layers going this way, or if I flip it and test it in this configuration, I expect it to behave differently. So basically, it starts behaving like a composite material, like a fiber reinforced composite material, and it will start developing. It has essentially a layered structure, printed layered structure, will have some level of orthotropy to it, orthotropic material behavior. And that's what we really need to get into to understand the orthotropy and how that influences the response of the structure.
One more question is there, sir.
Sure.
Regarding this thixotropic clays that is in the form of motamorphite clays you are using, sir, for the improving the thixotropy of the concrete. Is there any mixture of these thixotropic clays like motamorphite clays with sodium silicate? Generally, in the case of soil grouts, we use the combination of sodium silicate and the motamorphite clays as a combination with the cement slurry, sir. That improves the fluidity of the soil grouting mixtures.
So yes, I mean we are currently using nano clays which have highly refined nano clays are excellent. The problem is that these are very expensive. So nano clays, highly refined nano clays are very expensive. So what we have done in our lab is that we have used regular clays like bentonites. We've even used kaolinite. They work beautifully. In fact, the only thing is nano clay is very effective at 0.1%, 0.2% dosage. With regular clays, I have to use like 1 or 2%. So that is the only difference. But yes, we can use it. We've used it with sodium silicate when we are looking at geopolymer systems. So there we have used nano clays and clays with sodium silicate to give the buildability to produce the thixotropy.
Thank you, sir. Thank you for it.
Dr. Rao is our member of ACCE from Kakinada Center, sir. He is a very knowledgeable person. He is also consulting engineer, sir.
Okay.
Yes, sir. One question is there from Swapnil. What is the maximum size, length, and diameter of hose or pipe you have used for pumping of 4 mm size aggregates?
We have used about 30-meter hose, but longer hoses should be possible. Ours is basically a 30-meter. We've tried.
He also asked what is the diameter? Diameter of the hose also.
Yeah, that's interesting. I will have to check, but it's just a regular hose that we use for pumping of concrete. Yeah, I don't have the number readily available with me. I'll have to check that.
Okay, sir. I have a question, sir. Say, for example, one job is one on-site job is completed, uh, and we need to establish the same equipment to another on-site job, sir. Uh, is there any challenges in the robotics due to shape variation in the structure?
No, in fact, if anything, that's a big advantage because I can print any shape that you want me to print. So geometry is variations in geometry are very easily handled with this robotic printers. The challenge always comes, and this is where my students are always unhappy, is cleaning the entire system. Once you have pumped concrete, you have to clean the entire system. That is the hoses, the pumps, and the nozzle, everything. If you don't concrete sets inside, then you are in trouble. So that once you're done with the printing job, you have to clean up the system and get ready for the next job. And you can simply take your printer and start printing in the new location.
Sir, I have a question.
Yes, sir. Yes, sir. Carry.
Yeah. Is it possible to print the horizontal members like slabs and beams?
Horizontal, no. Horizontal is the Achilles heel where I can't have the material hold against gravity. So that's one of the biggest limitations right now. So what we can print currently is called cantilevering. So I can basically print an arch. So if you look at an arch, I can come vertical and I can print this. So what we start doing is we start cantilevering the material. So every layer, we basically give it a little bit of a ledge or an overshoot, and I can keep doing it till I get the whole arch. That can be done. But right now, horizontal, no, we cannot.
Okay, thank you, sir.
Yes, sir. I have one more question, sir. How many days approximately will take to dismantle the entire equipment to shift from one side to another side, sir?
It's about the same as what you would require for, say, concrete pump. So today, when we do have concrete pumps, and we have concrete pumps that are able to pump to good heights, so the shifting of the pump itself would be the same as that. In fact, I'll give a parallel. We do use slip forming, and slip forming is quite common even for say for constructing something like a silo. It's being used. So we have jump forms, slip forms that are available. So essentially, in terms of moving hardware from one location to another, it would be the same as the effort involved in moving a slip form from one location to another.
Is the concrete of yes, sir. Carry on, sir.
Sir, as you said, there is no support. It's not self-standing. We down and lift it once it sets the handling strength. So can we lift and keep it or as a? Can we use it as a slabs for the shorter spans?
Correct. Yeah. So that's actually currently that's exactly what we're doing. So the horizontal elements that we have, because we are not able to print them, what we are doing is either bringing in precast slabs and integrating precast slabs with vertical elements, or we can print formwork and essentially take the formwork and pour concrete on the formwork. So that's how we're doing horizontal elements. So this whole thing about printing offsite, I can offsite print anything and take it to the site and assemble it. I can do that.
Okay, thank you, sir. And what about the water tightness in the wet area?
Tightness of the joints is an issue, and that is one of those things that is being standardized. So we are trying to standardize the requirement of water tightness of the joints.
Okay.
Sure. Sir, what is the density requirement of the concrete, sir? Is there any?
Same as regular concrete. So basically, we get almost the same density.
Okay.
That doesn't change, yeah.
Okay, sir. Is the concrete need any self-compacting properties, sir?
No. In fact, I cannot have self-compacting because it has to come out and keep its shape. So once I extrude it, it has to be stiff enough that it keeps the shape. If it is self-compacting, it will not keep its shape.
Yes, sir. You touched the topic of this geopolymer concrete. Is there any limitations in this 3D printing, sir, using geopolymer concrete?
The mix becomes a lot more challenging, but it can be done. So we've done it. We have geopolymer concretes that can be printed.
What are the softwares, sir? Design softwares, sir? Any design softwares?
None. Right now, none. I mean, it is right now. When you say design software for what? Structural design or material design?
This regarding this shape printing and all, it related to
so currently,
structure to structure, sir?
Yeah, in terms of printing itself, nothing is standardized. So there's no software that is available commercially. Individual people who develop their own printing systems have their own software. So they will, if you buy a machine from them, they will give you their software.
Okay, sir. And in two-wall system into double wall system, the space between the walls to be hollow or to be filled up with any materials after construction?
You can fill it up with insulating material. So I can put something like glass wool to give thermal insulation. I can fill it with acoustically insulating material. The material that goes between the layers is up to us. We can even use the gaps between for chasing. So I can run my conduits and all these through the between the double walls.
Any questions from the participants, sir? Students? Hope students are there. Many students are there. Any questions from student side? Faculty? Field engineers?
Hello.
Yes, sir.
Sir, can we use it for the construction of the retaining walls?
Yes, in fact, one of the largest applications we're currently looking at is retaining wall and boundary walls. So we're doing a lot of boundary wall projects right now. Okay. In fact, a big boundary wall has been printed around Chepauk Stadium in Chennai, the cricket stadium. I think the whole boundary wall is around 3 kilometers or so. It's all printed with very nice architectural features. The entire wall was printed.
But the retaining wall parameters are different, no, sir? Because
so what we will do there is that we will actually print the shell, and then we can put reinforcement in there and fill it with concrete. So basically, it will form your formwork for the in-place concrete, and we fill it with concrete. It will speed up the job, the entire job of doing the printing.
What about the design, sir, for this?
Design the structural design of 3D printing has printed elements has not been standardized yet. So that is one of the issues that we do face.
Because again, we have waterproofing and
that is always a challenge. So that's why when it comes to retaining wall, what we can quickly do is we can print the 3D the shape of that, take it in the form segments and fill it with regular concrete. So that can be done. Or we can print the shell and we can even fill it with earthen elements and have an earthen rammed earth or something and create a retaining wall. So some interesting things can be done there.
Okay.
Considering the present technology, according to the present technology, we can cache the buildings. And you said that we can cache the bridges, retaining walls, and some boundary walls. And any other structures can be cached, sir, according to your knowledge.
Yeah. So I don't use the word cast. I think I'd say print. So casting is different than printing. But yes, in terms of printing, structures in India, L&T, largest construction company in India, has already demonstrated by printing a post office, which was inaugurated. It is printed in Bangalore. It was inaugurated. They are currently working on a very large project of printing a mall and some residential apartments. I think it's a 3 or 4 story residential apartment in, I think, around Chandigarh area. So that is another project they're working on. We are currently working with the army in developing or printing for them these bunkers. Essentially, they are protected structures. And the reason why printing is seen as a good solution there is because the bunkers should not be rectilinear. You cannot have flat surfaces. So to have blast, when it is subjected to a blast wave, a curved shape does better. So we can actually print curved shapes much easier. So therefore, it is an apt technology for them, and we're working on developing battle hardened structures for them. Remote printing in forward areas is something the army is very interested in. And of course, I showed you about bridges. So buildings, bridges, some protective structures, specialized applications, a lot of architectural applications. So we were looking at facade elements, facades, infill walls. Infill walls is a big application today. So we can quickly print infill walls of any shape, any size you want, and give you a double wall system that's very lightweight. And you can either fill it with insulating material. You can fill it with lightweight material like bentonite slurry, or you can fill it with foam concrete, so that you get the insulation, the thermal acoustic insulation. And you can also use that for the gaps between the walls. You can use it for chasing. So these are all different applications that are being actively looked at.
Great, sir. What are the research? What is the research is going on this technology, sir? According to your knowledge, in future, what we can expect in future in this 3D printing technology?
Future would be all those things I mentioned. So right now, we have not yet standardized the material mix procedures. The printing technology itself has not been standardized. What type of pump to use, what is expected from a pump, the placement systems, all of these have to be standardized. So they are being standardized today, because today we have 50 people working in the world. Everybody uses their own system. Development of the concrete mixtures. A lot of work is happening on how to develop concrete mixtures that will meet our requirement of pumpability, printability, and buildability. Then internal reinforcement. We are right now looking, a lot of people are working on how to integrate steel reinforcement or any reinforcement with printed structures. Then the durability aspect that is aptly raised is how durable are these structures? We have layers, we have gaps now between the layers. Now, can water get in there? How can we make it watertight? How durable is the structure? So a lot of studies are going on that. So a lot of things are going on concurrently on all of these topics. And hopefully another 10 years, we'll have answers. These things will get standardized. Then it will become technology that people can readily use a standard and to print a structure or for any other use that they see.
Any questions from participants side? Or else we will conclude the program. Hope there may not be questions from sir. This is time for my vote of thanks. My special thanks to today's speaker, Professor V.L.Subramaniam, IIT Hyderabad, for accepting our request and his valuable time with us. Thank you very much, sir. My sincere thanks to ACCE headquarters team for their encouragement and support by providing this WebEx platform. Thanks to our managing committee, ACCE members, faculty, co-engineer friends, participants from different places of India. My special thanks to our members for their support in this webinar organization, Sairam and Sunil. Thank you all. Thank you. Thank you. Sir. Thank you.
Thank you.